Okay. So how to write this set? This can be written as the set of all those x inside R such that x squared is less than 1. So how do you write this set? This is the set of all those x in R such that x squared less than x means what? X is x less than what? Plus minus 1 or what? Square of x is less than 1. So x is less than 1 or x is greater than minus 1. Is it or just see nicely? I want x square greater than less than 1. So x square will be less than 1 if x lies in which area? This is 0, this is minus 1. In which portion square of x will be less than 1? If you write it this way, x less than 1 or x greater than minus 1, so x equal to 5 may also satisfy this. X equal to 5 satisfies this. X is less than 1 or x greater than minus 1. So x equal to 5 satisfies this, but it doesn't satisfy this one. Okay, so it's not or actually, it's and. If x squared is less than a, x lies between minus a and minus root a and plus root a. So here it will be x belongs to R such that x less than 1 and x greater than minus 1. So that means this is actually the open interval minus 1 to 1. Okay. All those real numbers which lie between minus 1 and 1. Okay, so this is an open interval. Okay. So we have already seen the result that every open interval is an open set. Okay. So this is an open set. So this is an open interval, which is an open interval and hence is an open set. This is an open interval. Open interval. And so is open. It's an open set. Every open interval is an open set. The other way it is not true. There are open sets which may not be open interval. Clear? How to do this? So similarly, the next one is it is the set of all those x inside R which satisfy x squared plus twice x minus 15 is greater than 0. So simplify this. It is x square plus 5x minus 3x, middle term factorization, minus 15 which is greater than 0. Put it. 5 to the 15, middle term. So I can write this as the set of all those x inside R such that x into x plus 5 minus 3 into x plus 5 is greater than 0. So this will be set of all those x in R such that x minus 3 multiplied with x plus 5 this is greater than 0. Now what can you write? X minus 3 multiplied with x plus 5 is greater than 0. So what is this set? X minus 3 into x plus 5 is greater than 0. So, x minus 3 into x plus 5 is greater than 0. X. So, this is 1.3. X minus minus 5. So, minus 5 is another one. Okay, somewhere here. Minus 5. So the product of these two is positive. That means both are positive or both are negative. Okay. So if x is greater than 3, x is automatically greater than minus 5 also. Okay. So either x belongs to this part, okay, or if x is less than minus 5, then it is also less than minus 3. Okay, so both will be, if x is less than minus 5, x minus minus 5 will be negative. Okay. And similarly, if x is less than minus 5, it is automatically less than 3. So x minus 3 will be negative. Okay. So the product of two negatives will be positive. So these are actually standards we have done in height symmetry. X minus alpha into x minus beta. If it is positive, then x lies between. X belongs to, say, alpha is greater than beta. Then x belongs to alpha comma infinity union with minus infinity to beta. Okay. So this result actually. And x is either greater than alpha or less than beta. So this is what you write. So I can write this one as, it is the set of all those real numbers which satisfy x is greater than 3 or x is less than minus 4. And what is this in terms of interval? I can write this as minus infinity to minus 5 union with 3 to infinity. Okay. So this set, the second set, is a union of two open intervals. Okay. And we have done last day that union of two open intervals will be open. Okay. This is an open set, this is an open set, their union is open. Okay. So union of open intervals, which is a union of open intervals. Okay. And hence it is open. So which is the union of two open sets. Open sets. Okay, hence it is open. Hence it is open. X greater than x less than, their product is positive. So one case is x minus 3 is positive. So when x minus 3 is greater than 0, this will imply x is greater than 3. So when x is greater than 3, x is also greater than minus 5. Okay. X is greater than minus 5 also. So x minus minus 5, this is also greater than 3. So their product is positive. Okay. So either it is x greater than 3 or it is x less than minus 5. Okay. If it is x greater than minus 5, it means, say for some point here, say minus 4, you will try, this will not be satisfied. Minus 4 minus 3 multiplied with minus 4 plus 5. Okay, this will give you negative. Okay. So it has to be x less than minus 5. Okay. If x is less than minus 5, then this will imply that x plus 5 is negative. Okay, and x is less than minus 5 means x is less than 3 also. Okay. So x minus 3 is negative. So both are negative. Their product will be positive. So that is why this happens. So it is greater than the larger one or smaller than the smaller one. Okay. That is the thing. Right. Okay. So if it is here, if it is negative, if the product is negative, it will lie between these two. If x lies between these two, then your x plus 5, this is positive, and x minus 3 will be negative. So their product will be negative. So if it is negative, then x will lie between minus 5 and 3. So just open interval minus 5. So here it is, the union of these two open intervals. Clear? Okay. So the next one, number C, how to do it? This is also simple. So number C equal to set of all those x in R such that x squared plus x minus 6 equal to 0. So it is the set of all those x inside R such that x square plus 3x minus twice x minus 6 equal to 0. So that is set of all those x in R such that x plus 3 into x minus 2 equal to 0. So what is that? It is the set minus 3, 2, which is a finite set. So this set cannot be open which is not open. Which is not open as it cannot contain any interval. This set cannot contain any interval. This is a finite set having only the points -3 as it doesn't contain any interval. Doesn't contain any interval. For open set, for every point inside this set, we should get at least one open interval which is inside. Okay, so this set doesn't have any open interval, so there is no chance that this will be open. It is not open. Okay, so the first two are open, the third one is not open. An intersection of open sets, these things also we have done. Okay. So next we come to a concept called limit point. Limit point of a set. Okay, so in particular any finite set can never be open. Is 1, 2, 3, 4 like that up to say 1000, 10,000 or 1 lakh. Okay. So this is not an open set, not open. Right? It is not never an open set because it doesn't contain any interval. Okay. So next concept is the concept of limit point. Limit point of set. Point small x inside R is said to be a limit point of a non-empty set A of R if every epsilon neighborhood of x, epsilon neighborhood of x contains at least one point of A, one point of capital A different from x, different from x need not be a point of x. Okay, limit point of a set may be a point outside the set. Need not be a point of this small x is not necessarily a point of capital A. Okay. So a point x in R is said to be a limit point of an non-empty set capital A subset of R if every epsilon neighborhood of x contains at least one point of A different from x. Okay, it may happen that x is inside A also. Okay. So we should make sure that this small x will be a limit point of say some set capital A if every epsilon neighborhood means whenever you draw this type of neighborhood x minus epsilon to x plus epsilon, every epsilon neighborhood it will contain some point of A, okay, other than x, okay, different from x. So if I draw here also, then also I will get some point. Okay. Whatever open interval you draw, always you will end up with some point inside the set capital A. Okay. So this actually basically means that the point x is very close to the set A. Okay. So something like this. If you have this open interval, say open interval 0, 1. Okay. So keeping 1 as center, if you draw any open interval, Okay. Keeping 1 as center, if you take any neighborhood, then it will always contain points inside this set 0, 1. Okay. So this point 1 is a limit point of this particular set. Okay. Every epsilon neighborhood contains at least one point of the set other than 1. Okay. This is it. So geometrically also you can see this point 1 is very close to this set. Okay. So however, say 2 is not a limit point, or say something like 1.1. This is not a limit point because you can easily draw one open interval like this. Okay. Which does not contain any point of 0, 1. Okay. Because there is a large distance between 1 and 1.1. So we can easily construct one open interval which does not contain any point of this 0. Right? So a point is not a limit point if there exists an epsilon neighborhood of x which contains no point of capital H, okay, other than x, okay, other than possibly x. It is a limit point if every epsilon neighborhood contains one point of it. Okay. It is not a limit point if there is a neighborhood which does not contain any point of it. Okay. Just logical idea. Yes. The points inside this set for this open interval, it is always a limit point. Because it's an open interval itself. Whatever interval you draw here, okay, that will contain points of this 0, 1. Okay. So, but this is for this set. It may happen that it is not necessary that every point inside a particular set is a limit point. Okay, that is not necessary. Because if you take a set like this, say 1, 2, 3, this set does not have any limit point. This 2 is not a limit point of this set because I can easily draw this. Keeping 2 as center, if you take say something like 2.5 to 1.5 to 2.5, this open interval, this does not contain any point of this set. So 2 is not a limit point of this set. Okay. So it is not necessary that every point inside the set is a limit point of the set. Okay. In particular for this interval it is true. In the interval every point is a limit point. Right. So we will see how we can deal with these things. So in particular finite sets do not have any limit point. Okay. That also we will see. Finite set cannot contain any limit point. Okay. Because whenever you take a finite set, you can easily draw open intervals which do not contain any point of this. Okay. So here you see this open interval contains the point 2. Okay, but I want something different from 2. Okay. Only 2 contain every open interval containing 2 should contain at least one point of the set different from 2. Okay. If this is not included, then every point will be a limit point. Okay. That is why this is included. If I do not include this, then here 1, 2, 3 all are limit points. So this restriction is important. Different from x. Okay. So symbolically we write it this way. Symbolically we write x is a limit point of if for every epsilon greater than 0 we have this open interval, epsilon neighborhood, x minus epsilon to x plus epsilon. This intersection with a difference x is non-empty. A difference x. From A, I remove the point x. If x is not there, then no problem. It may happen that x is inside A. Okay. So we have to separate that point. So symbolically, this is the definition. X is a limit point of A if for every epsilon, this epsilon neighborhood intersection with A difference x is a non-empty set. Okay. That means at least one point is there inside this epsilon neighborhood which is a point of A other than x. So that is the symbolical expression. Yeah. Okay. Then what is the derived? What is the derived set? Derived set is derived set. Let A a subset of R. But here I have defined it for non-empty set. So for empty set, actually, what are the limit points of empty set? Empty set, the limit points, there cannot be any limit points because for limit point I need that at least one point of this set. I should get at least one point of this set in question. Okay. So if A is itself phi, I cannot find such a point. Okay. So no epsilon neighborhood will contain at least one point. So that means the empty set phi cannot have any limit points. So we can say that phi has no limit points. So let A subset of R. So we can actually we can remove this non-empty part. We can remove this. Okay. It will not highlight. Okay, just remove this part of a set A subset of R. That is enough. Of a set, just remove the non-empty part. Okay. Otherwise, again we have to write separately. So from the definition, just remove non-empty part. The empty set is automatically not satisfying this condition. Okay. So no real number can be a limit point of the empty set. Okay. So I don't have to write non-empty here separately. So let A subset of R. Then the derived set of A. The derived set of capital A is the set of all limit points of capital A. All limit points of the set of all limit points. Okay, it may happen that a set has many limit points. Okay, so you take the collection of all limit points, then you will get what is called the derived set. So let A subset of R, then the derived set of A is the set of all limit points of A. Okay. It is denoted by derived set of A, the DA. Okay. Derived set of A. Yeah. So the set of all limit points of capital A is called derived set of A. So now let us try some examples. Some easy examples of limit points. Number one, a derived set of R is R. What will be the derived set of R? The set of all limit points of the set of real numbers. It is R itself. Okay, because why derived set of R is R? Because every real number x is a limit point. Every real number x is a limit point of R. So how do you justify? How do you justify that every real number x is a limit point of R? Because as x minus epsilon, x plus epsilon. Okay. If you take any open interval containing x, okay, any epsilon neighborhood of this, it will always contain points of R different from X. Okay. So for as this intersection with R difference singleton X. Okay. So this is always non-empty. Not equal to 5. Right. Say in particular, so this is not equal to 5 for every epsilon greater than 0. Whatever epsilon you take, this set, this intersection is never empty. Okay? Because you see this one, x minus epsilon to x plus epsilon. Okay. Epsilon is a positive quantity. So can you find a point inside this interval? Inside this neighborhood, can you find a point which is different other than x? One point inside this interval which is different from x. X plus? Yeah, x plus epsilon by j. You take some point here. Okay. So something like x plus epsilon by 2. Okay. Or say something like x minus epsilon by 2. Okay. X plus epsilon is not a point here because it's an open interval. Okay. But easily we can find other points inside this interval. Okay. So this x plus epsilon by 2, this is not equal to x because epsilon is non-zero. Okay. So if it is equal, then x epsilon becomes 0. Okay. So this is a point which is different from x. Okay. And since the set is R, this point is a point inside R. Okay. So this is quite obvious as this is not equal to 5. In particular, x plus epsilon by 2 is a point inside, is a point in the above intersection. It is just sufficient to find at least one point which is different from x and lies inside this set. Okay. That means what I have proved? I have proved that every real number is a limit point of R. Okay. So that is why derived set of R is R. Okay. Every real number is a limit point of R. Clear? Every real number is a limit point of R. Okay. Then another example is just now that I had said derived set of phi is phi. Number 2 is derived set of phi is phi. Because phi has no limit points. As phi has no limit points. So the empty set doesn't have any limit point. It doesn't satisfy the definition of point. No point can be a limit point of the empty set. So derived set of phi is phi. Okay. Number 3. Say derived set of this set. Say 1, 2. Okay. What is this? This derived set of this finite set 1, 2. This is also empty. Okay. No number can be a limit point of this set. Okay. We will just justify. We will justify this. If you have the set 1, 2, this is a finite set having 2 elements. This set cannot have limit points. So how to justify that? Okay. So see, this is the real number system. 1, 2. Okay. Suppose I take a point x here, and I try to construct. Say I take a point x here. Can I construct an open interval, an epsilon neighborhood which doesn't contain any point of 1 and 2? Huh? We can easily construct. See, from the diagram it appears it's quite easy. Huh? So what I have to do is actually I have to take. So how do I construct this type of interval? in your school days you have done compass. A compass tie in a box. Here you mark one, okay, and then rotate and again mark one. Okay. So this is how we construct epsilon neighborhood. Okay, very simple. So this x is the center of the epsilon neighborhood. Okay. So if I construct something like this, whose distance from 2 and distance from 1, okay, is much less than this distance. Okay, distance of x from 2 and distance of x from 1 is also distance of x from 2 and distance of x from 1 is much greater than this distance. Okay, then whatever interval I construct, this interval will not contain the point 1 and 2. Okay, so that is the idea actually. So if x lies here also, see, I can construct a open interval of this type. I will take the minimum of these two distances. I will take the radius in such a way. If I take this radius, then there is a problem. It will not contain this. Right. Sorry. Means if I take this larger radius, it will contain some point of capital A. Okay, but that doesn't matter. So some point of it matters actually. Some point of capital A different from x. If I take this distance, large distance. Okay. If I take this distance, this open interval will contain the point 2. Okay, which is different from x. So this will not work for us. Okay. So what I have to do, I have to take this distance, smaller distance. Okay. If I take the smaller distance, then the open interval that I construct, it will not contain 2, it will not contain 1 also. Okay. So that is the idea. Right. So that's how we will show. So when x is on this side also, the same thing. Okay. We will take distance which is the minimum of these two distances. Okay. We will construct an open interval such that the distance is minimum of these two distances. Okay, then it will not contain the point 1 and 2. So how to show this? Derived set of this is 5. So let x belongs to R be any point. We will show that x is not a limit point of 1. We will show that x is not a limit point. Of this set point. That means not a limit point means there is some epsilon neighborhood which does not contain any point of 1. Okay, that is what. So let epsilon equal to minimum of the distance between these two, x minus 1 and x minus 2. Okay. These two distances. Epsilon is minimum of these two distances. Right. So we construct an open interval. We will construct one open interval, x minus epsilon to x plus epsilon. So then the open interval, the epsilon neighborhood, x minus epsilon to x plus epsilon does not contain any point of this set point. Right? We have constructed an epsilon neighborhood which does not contain any point of 1. Hence, x is not a limit point. X is not a limit point. Of 1. Okay. So we have selected an arbitrary real number and we have seen that it cannot be a limit point of the set point. Okay. Clear? Okay. So 1 doesn't belong to this, 2 also doesn't belong to this. Okay. Any point which belongs to this will satisfy y minus x is strictly less than epsilon. Okay. So 1 cannot be a this point inside this set because 1 minus x, this is not strictly less than minimum of this one. Right? Either 1 is a point inside this set or in the, sorry, 1 cannot be a member of this set, 2 also cannot be a member of this set. Okay. Clear? Right? Because this is an open interval. No? This x minus epsilon to x plus epsilon. This is an open interval. Okay. This is an open interval. So 1 is not a member of this interval because the distance between x and 1 is what? It is exactly this. Distance between this x and 1 is exactly x minus 1. Okay. But for any point inside this open interval, the distance between x and y is strictly less than epsilon. Okay. So it cannot be exactly epsilon. So 1 cannot be a member of this. Okay. Right? So direct set of this is pi. So we will see some other examples as well. What is the time?